Okay guys, welcome back. We are continuing our discussion of BGP. In this particular lesson here, we're actually going to be talking about working with iBGP, specifically on how do we increase or add efficiency to iBGP by either creating route reflectors or using BGP confederations. We've already talked a little bit about the route reflector technology and the basic concept, but I do want to go through some of the other details, and then we're going to get into a discussion of confederations as well, talk about the differences, why I might choose to use one versus the other, or maybe in a particular case I might decide that I'm going to go ahead and use both, right? Route reflectors and confederations. So that's really what we're talking about in this lesson, or what are our iBGP scaling techniques. We're not actually going to take a look at any configurations in this lesson. We will take a look at some configurations in a couple of our future lessons. So we're specifically focusing on route reflection and how large-scale route reflection works within a large route, using large route reflection clusters. And then we're going to talk about, towards the end of the lesson, what is a confederation, talk about, like I said, what are the differences with confederations and why I might choose one over the other. Okay, and in our probably the next couple of lessons, we'll go through other sections of implementation examples for both of them, and so on. As we talked about in our last lesson, the overall idea of either of these is to eliminate the need of having some sort of full mesh in the design. You know, when we talked about iBGP peering relationships, we talked about the need to have a full mesh in order for us to be able to exchange the reachability information between our peers. And because we're not technically utilizing those advertisements to define the data plane path, we still have to maintain a complete control plane database of the BGP table. And so scalability issues come into play when we're dealing with full mesh iBGP, because it's exponentially going to require that we have more and more peers, and it's just not really feasible to manage all those peers individually. So instead of all the routers having to peer with one another, we just simply peer with a centralized route reflector if we're using the route reflector design. The ultimate end result is much like how like an OSPF designated router works in multi-access networks, or how the ISIS designated intermediate system router works in an intermediate system design, where we have a router that's managing the control plane and propagating or repropagating information about the control plane without the need of actually acting as part of the data plane. There are obviously some design considerations. Because we're not doing a full iBGP mesh, one of the things that we have to concern ourselves with is how do we now facilitate loop prevention, right? Because traditionally with iBGP peers, it's very simple. I'm not going to advertise a route to one iBGP peer that I learned from another iBGP peer. But because we're kind of breaking that design without having a full mesh, we have to have other mechanisms for managing that process. We'll talk about that in a little bit, okay? Whether I decide to use route reflectors or confederations really is going to depend on the design of the overall network. Most practical designs, the route reflector is not going to be in the data plane path. They're just going to host the routing table, and then the clients will use their IGP, or they're going to use MPLS to route the traffic. And this is really critical when we think about the overall design and where we place our route reflectors in the topology, and whether or not we even run a physical box, right? We can actually run virtual route reflectors. We'll talk about that a little bit later on. We know that the idea of doing a full mesh in iBGP is for loop prevention. The iBGP route reflection loop prevention mechanism needs to be in place because we're now breaking that overall design. So how does a route reflector manage this? How do we maintain or ensure a loop-free topology if we're implementing a route reflector? This is where the cluster ID comes into play. It's a really simple concept. It's kind of like a tag, if you will, or a way of identifying the source of particular prefixes that are being advertised. But it's similar to the concept of AS path with eBGP peers, where the route reflector is going to drop any routes it gets that has its own cluster ID listed in the attributes. Okay, so we're actually identifying what cluster the routes are coming from, and if I end up seeing my own cluster ID in the attributes, then I'm going to go ahead and simply ignore those particular updates, if that makes sense. We'll talk about, there's actually an originator ID as well as a cluster ID. We'll talk about the difference between those. We'll take a look at those in our design or when we do our implementation later on as well. Okay, so we'll talk about that. But it's typically going to be the router ID, and that will allow us to maintain this loop prevention capability within the cluster design. Now, the clients themselves are going to use the originator ID for loop prevention, and we'll talk, like I said, we'll talk about that. We're actually going to do, when we do our configurations, we'll actually do some packet captures, and we'll take a look at where those values show up in the database or in the actual packet itself, and how we can then use that information to identify the origination of the routes, and in addition, ensure that we're not going to have any kind of loops in the topology based on those origination IDs. All right. With regard to route reflector peering, route reflectors can actually have 3 different types of peers. We talked about this a little bit. I think I still have the diagram actually. We talked a little bit about this when we were kind of going through this particular diagram here. Okay. Although it's not reflected, pun intended, in this particular diagram, we can have 3 different types of peers with route reflectors. We can have traditional eBGP peers. We can have what we call iBGP client peers. And then we can have something called an iBGP non-client peer. All right. The difference between them is the route reflector process, how we process updates. It's going to be different depending on what type of peer the route came from. For example, eBGP peers pass traffic to other eBGP peers, and they can also pass traffic to clients, and they can pass traffic to non-clients. So essentially, we're not restricted on what kind of information we can pass back and forth with eBGP. A client is the same, actually. The client can pass traffic to eBGP peers. It can pass traffic to other clients and non-clients as well. The only one that's really restricted is the non-client. The non-client can only pass learned routes, to the route reflector and so on. All right. We can pass traffic to eBGP peers. We can pass traffic to clients, but non-clients cannot pass any traffic to other non-clients in the design. All right. There is a specific reason for this particular rule. It has to primarily do with large-scale BGP designs where the route reflector and how we place those route reflectors in the topology. We're not really going to get into that in our environment because certainly you're not going to see a large-scale design on the exam. It's just not feasible. We may, there's some documentation that I'm going to reference for you guys a little bit later on. We'll pull some documentation up as well and talk a little bit about, where you can find additional information about large-scale BGP designs. In most practical designs, you're also not going to have a single route reflector. I think Mike had talked about this last time when he was participating. So we typically will place the network or design the network at least into 2 different clusters where the cluster is made of some sort of physical topology of the network. But let's say I'm running, for example, a topology where I have I'm covering the United States, and I've got the US from the West Coast to the East Coast, where I might have a cluster in Los Angeles, a cluster in New York. Maybe I even had something in between, like in Chicago. Then we're going to do some sort of inter-cluster peering between them in order to advertise the routes between those particular clients. Ultimately, though, and I think this makes sense, you don't want the whole network to rely on one control plane. You want to have some redundancy built in. So adding the redundancy by having multiple clusters does two things, right? It provides that redundancy for failover if necessary, but it also provides a level of hierarchy. And we can, create a design that is scalable based on that hierarchy. All right. The cluster itself is simply going to be a combination of a route reflector and its clients and the other route reflectors using the same client identifier. All right. If you go, let me see if I can find this document. I meant to pull it up ahead of time, but I'm sure we can find it here. If I go out to Google and I search for, what do I want? BGP Design Guide. Spell it right. Yeah, this is the document I'm looking for, BGP Case Studies. Now, this document will, it's a great document actually, because it talks about all the stuff that we've talked about from the beginning with regard to BGP. eBGP versus iBGP. What are some of the limitations? What are some of the considerations? It's not loading. There we go. But one of the concepts, right? So what is eBGP versus iBGP? How does BGP work? But if you scroll down and we look at the route reflector section, right? So they go into this, into some very basic route reflector concepts, and that is creating iBGP peering with route reflectors. In this case, router A can send its information to router C as the route reflector, and router C can send its information to router B. But in a traditional design, without this route reflector configuration, router A and router B would have to have some sort of peering relationship. All right, this is a really, really basic concept, right? And we can see here, we're just simply going to implement the command neighbor route reflector client. And that's the command that allows us to identify the route reflector. And we specify that. Well, again, we'll take a look at this in the configuration a little bit later on. But notice that would be something that we're going to create. Let's see, the route reflector with this command is the route reflector, and the neighbors at which the command points are the clients of the route reflector. Okay, so router C in this case would be configured with neighbor route reflector client, and then that's going to point at router A and router B IP addresses, and this constitutes the cluster. All right, again, in this case, other iBGP peers of the route reflector are not clients, they are called non-clients. So this is an example where we have multiple route reflectors. This might be LA, this might be Chicago, this might be New York, and we have now multiple clusters where we're sharing information. We know that within the autonomous system we can have multiple route reflectors. Remember, this is still all iBGP. And our goal in this case is, of course, to get rid of this full mesh requirement, where all of these routers would have to have peering relationships with each other. Okay? So this is a great document to take a look at because it does talk about different design scenarios. It's pretty light reading, compared to some of the other documentation that exists. And it does describe, the configuration, how I would configure each peer and so on. And we'll of course talk about these designs. This would be, of course, on the route reflector, and we're simply identifying router 2, if you will, and router 1 as clients to router C, which is acting as a route reflector for that topology. Notice router B in this particular case is not configured as a route reflector client because if you look at the topology, router B just gets a standard configuration. Only the route reflector client has a unique configuration to the topology. All right, so this is a great document, and it talks about having multiple route reflectors within a cluster for redundancy. This is typically where you're going to be. You've got long haul circuits that might be connecting each of these route reflectors, and then you have your local regional connections that would connect the clients to those route reflectors. But for example, router F here, if router D were to go down as a route reflector, we would lose connectivity with router F. So we'd want to make sure that we have a secondary route reflector within that cluster to provide services for that particular route reflector. So there's all kinds of options here. It's a great document to take a look at, specifically for each of the topics. If I go back to the beginning here, this is just the route reflector piece. But if I go back to the beginning here and take a look at the table of contents, you can see it pretty much goes through just about everything that we talk about with regard to BGP. So excellent document. And I would highly suggest that you take a look at this. All right. Now, with regard to different designs, not all there's not one design that's 100% right or wrong. It actually does depend quite a bit on other factors in the topology. Like I said, usually the design even goes a bit further than what you're typically used to seeing, where you have, like, we would have multiple route reflectors servicing the same client for redundancy purposes, and we would have, say, a client reflecting with reflector 1 and reflector 2. From an implementation view, it makes it a little bit more complicated, right? Because we don't necessarily want to learn the same route from the client on route reflector 1 and route reflector 2, and then have route reflector 2 learn that same route from route reflector 1. I mean, the end result is the same, right? We still learn about the routes, and we won't have any loops of the updates for the routes discovered, because when I do get the route from the client with the originator ID being specified, if I were to get that same route from route reflector 1, being on route reflector 2, I would simply throw it away, because the originator ID is still going to be the client itself. But we do tend to be utilizing more control plane functionality, and of course we're still using data plane resources to be able to process that information. So it does get a little bit more complicated. That BGP case study document does go into describing some of the design considerations from that perspective as well. So definitely something that you should take a look at. All right. The other thing to note that's important to know about route reflector pairs is that they're only going to service one address family. There's a feature, or not a feature, an issue that we have within BGP called fate sharing of services, FATE. And I don't need to get into the specifics of that, but the idea is that if I have a service provider that's doing address family IPv4 for the global internet, and we're doing that for the routing table, but we also have some sort of layer 3 MPLS VPN customers, we don't want some issues with flapping or other things happening in the global routing table to affect our MPLS customers. So in most typical designs, you're going to have a set of route reflectors for your VPN v4 MPLS network. You're going to have a set of route reflectors for your IPv4 unicast network, for your IPv6 unicast network, so that you can keep the services out of band from each other so they don't affect one another. Okay? And you might have some sort of intercluster peering between route reflectors. They can be clients of non-client. We can have clients of non-client peerings as well. It really just depends on your overall redundancy design. All right. So there isn't one design that's 100%. Hey, this is the golden goose, if you will, for route reflector design and intercluster design. If I am getting duplicate routes, it may mean that I'm doing more processing, even if everyone has a unique cluster ID. But again, we're still getting rid of that looped topology. Okay? Since we're using the cluster ID as part of the update, I'm going to know whether or not I should drop routes that I originated that get reflected back to me. Okay, so that cluster ID component, and again, we'll take a look at that when we do our Wireshark captures in one of our future lessons, but the cluster ID is going to be based on the router ID. By default, all route reflectors are typically going to be in separate clusters. But that's not always going to be the design case. It really depends on the physical topology. Am I going to use the same cluster ID on both clusters? Am I going to have a unique cluster ID? And when I say it depends on the design, I'm talking about the redundancy design, right? If a peering goes down, how can I indirectly learn a route from another cluster? Most people will consider, because clustering is a virtual concept, that we build clusters based on logical topology or logical design of the network topology, and that's actually not the case. It actually depends on the overall physical design of the network, and cluster peering should follow the physical design of the topology, not the logical design of the network. It doesn't make sense, for example, if I've got New York to Chicago to LA, and there's only one circuit path between New York and Chicago and one circuit path between Chicago and LA, to have some sort of redundant cluster between New York and LA, right? Because if there's a physical path loss, it's not going to matter that we have overlapping cluster configurations between New York and LA. All right? So we do want to design based on the physical design of the network, not the logical design of the network. We also have a new feature, relatively new. It's been around for a few years, called the virtual route reflector. Since the route reflector is not in the data plane or not in the data plane path, that means essentially that we're advertising the route to the route reflector. The route reflector sends it back to another client, but one client is not necessarily going to use the route reflector for the actual forwarding of the data plane packets. I will basically one client will basically generate a packet and send it directly to the other client. So this means that we don't necessarily have to have dedicated hardware boxes in order to use for the route reflector. We basically need to do something that has a lot of control plane resources, not necessarily data plane resources. So what we tend to do is use virtual machines for this now. I don't know if you guys are doing any of these implementations today, but we can use something that has at least a lot of memory, a lot of CPUs, and a VM can do this, right? You can use an iOS XRV, a CSR 1000V, Quagga Linux box if you want, hosting some sort of BGP table or whatever. Remember, the ultimate job of the route reflector is to advertise the routes on to the other clients. I don't need to install those routes in the forwarding table because I'm not going to be in that data plane. All right. This also goes along with something called the selected RIB download feature. Selective RIB download feature. Let me pull that up. This is another document that you should probably take a look at. Selective RIB download feature. All right. And I mean, it's a fancy term to basically describe essentially the fact that we're managing the control plane, but we're not doing anything specifically with the data plane. All right. It's used in the case where we have a physical box. We want it to be our route reflector, but we don't have enough resources on that physical box to forward the updates in the data plane or forward packets in the data plane. All right. We would see this typically in a design where maybe it's an MPLS layer 3 VPN, depending on the provider, right? Let's say I'm connecting to L3 or AT&T or whatever. They could have millions or even tens of millions of routes compared to the normal IPv4 unicast routing table, which is only about 500,000 routes. The idea is that the routing table gets so large that we cannot install the updates at the line card, but we don't need to, right? The idea is that we aren't in the data plane, so we don't really care about what gets installed into the RIB or the FIB because all we're using the router for is control plane processing and NLRI reachability information. So as long as we can install the information into the BGP table and advertise them on, that's all we care about. We don't need to ping the destination. And there's a component called the BGP table map. I'm not sure if it's, I mean, I'm sure it's listed in here. Let's see, yeah, the BGP table map that talks about how we filter out specific routes. We'll take a look at this in one of our other sections, the selective route download component. Essentially, it's a way for us to apply a filter to a BGP peer. All right. All right. So we're, excuse me, we're basically hosting the BGP table in the control plane, but we are not providing any features or any functionality for the data plane function. All right. Meaning we can't actually forward packets there. Now, conversely, we have something called a BGP Confederation. Now, ultimately, route reflection and confederation are going to provide essentially the same services. All right. It's going to reduce the need of a full mesh with iBGP, which is a typical iBGP requirement. But rather than having a central point where we reflect routes, we split up our autonomous system into something called sub-autonomous systems. All right. So it's almost like creating a bunch of smaller eBGP peering relationships within a single autonomous system. All right. Now, within the sub-AS, we still have the requirement for a full mesh, or at least some sort of route reflector configuration so that we can eliminate the need for that full mesh. So we can mix technologies here by creating these confederations, and then within the sub-AS, we can set up route reflectors, or we can do a full iBGP mesh. All right. So when I'm communicating from one sub-AS to another, that's going to act like an eBGP relationship. So instead of having a central point like a route reflector, we're basically breaking up the network into smaller pieces. All right. Now specifically, and we'll see this in the configuration later on, these are not eBGP peerings. They're called confederation eBGP peerings. And the reason I distinguish that is because there are some specific behaviors of the attributes that are a little bit different than eBGP. One of the most important attributes we've seen within BGP is the next hop attribute, and we do not modify that next hop attribute with sub-AS interaction like we would with an eBGP, traditional eBGP interaction. Okay? Now, devices outside of the confederation, they don't really know about the internal structure. The sub-autonomous system numbers get stripped off from any advertisements. If I am actually going to a true eBGP peer, I'm not going to advertise the sub-AS information. So I might be peering, for example, as an MPLS VPN customer with level 3. They're running a confederation internally. I don't need to know those details. So when I actually advertise my updates to the eBGP peers, or when they advertise their updates to me, they're going to remove that sub-autonomous system information from those updates. AS path is going to look like just one global AS. That's the only thing that I'm going to see. All right. Because these sub-autonomous systems are not publicized and we don't really need to know about that in the global routing table, we typically will use private ASs for the sub-autonomous system numbers in our configuration. Remember, that's AS 64512 all the way up to 65535. All right. One of the other big benefits outside of what we wouldn't see with route reflectors is the advantage of a confederation is that we can use different IGPs within the sub-autonomous system. So we could do an eBGP confederation on the edge, but make it look like one AS when we go and route globally. But within the confederation, we can create these different domains. So maybe I've acquired another organization or another company, and I don't have the resources or the ability to merge those companies. I could create a confederation and just maintain different IGP routing domains within the confederation and still maintain my routing. So that's a very useful use case scenario. Okay, remember, we strip off any confederation autonomous system or private autonomous system information when we leave the confederation. All right. There are other attributes, by the way, that are not modified when we move between sub-autonomous systems. Next hop, obviously very, very important. Confederations will not update the next hop values, so on our perimeter routers, we do need to do the next hop self attribute. And we'll see this in our design discussion when we go into the designs later on. Some other values, local preference, multi-exit discriminator. Those are going to be kept across sub-AS eBGP peerings as well. All right. Now we are removing the need for a full mesh, just like we saw with route reflectors, but we still need to account for some sort of loop prevention. Now in route reflectors, we use originator ID, cluster ID information to be able to identify or at least to prevent loops in those domains. In confederations, we have two other things. One's called an AS confed sequence. The other is called an AS confed set. I'm not going to get into the details of those right now, but these are intra-confederation properties. They never leave the confederation. They're non-transitive attributes. So just like multi-exit discriminator, non-transitive means that the attribute is processed between eBGP peers, but it's not sent on to the rest of the domain. Okay. How loop prevention works has an implication on the best path selection process. Now we're talking about what we used in iBGP, right? We just had an internal AS path, and iBGP peers would not update that AS path, right? Because AS path attributes means that we're going from one autonomous system to another. In the case of confederations, we're going to make a decision. Do we want to make the routing decision based on the total length of, in this case, the confederation sequence, or do we want to treat it as one overall autonomous system? I don't know that we'll get into those specific details when we get into the design and implementation, because we could talk about hundreds of different design scenarios and still not scratch the surface. It really does depend on what your physical topology look like. Okay. So both route reflectors and confederations accomplish the same goal. Why do we need both? The only difference between them and why you would choose one versus the other has to do primarily with the migration path. When you're configuring confederations, this is a very disruptive change because you actually have to change the autonomous system information. So if I've got a router that's going to act as part of a sub-AS, I actually have to get rid of the old BGP process and change it to a sub-AS process, which means I have to actually reset the BGP process. With route reflectors, we can actually migrate through without having to drop the data plane. Set up my peering, set up my route reflectors, and so on, and then I can change BGP attributes to decide how I'm going to route to a particular destination. So there are some cases where one is better than the other. If you're in a greenfield environment, you might decide that a confederation is more appropriate. If you've got a already deployed large BGP autonomous system or BGP design, route reflectors might be the better choice. In some cases, confederations are easier to manage because you're actually breaking up the network into smaller pieces. But you can also mix the solutions. Okay, you could say I'm going to have a confederation, but I'm going to use route reflector services as part of a sub-AS. All right, because you do have the requirement within the sub-AS, within a confederation configuration, you do have that requirement to either have a full mesh or to have some sort of route reflector configuration. All right, so we're going to wrap up this lesson. I told you it was going to be pretty short today. There are some great resources. Let me see if I can find them real quick for you. I was looking at these documents a couple of weeks ago. BGP at 18. Oops. This is a Google Talk. It's actually by Yakov Redker, who is the code designer of BGP, and it's a great document or great video. Talks about protocol design, and I guess it's referenced here a few different places, but it's probably this one here, Google Tech Talks. It's about an hour long. I would say if you have a chance, take a look at that today, or before our next lesson. It's a little bit older, but it's a great discussion of BGP. All right. Now the other thing is also Cisco Live 365, specifically BRK, RST, what was it? 3321. There it is. Scaling BGP. Okay. Also another great lesson here. Scaling BGP. And this is also a lesson on, obviously, from Cisco Live in 2016 on how do we scale BGP and so on. So two different resources I definitely suggest you guys take a look at. Remember, BGP is going to be a core technology on this exam. It's going to be a major component of both the written exam and the lab, even if you decide to take the new version of the lab later on. So this is definitely a good document. There's a video that corresponds with this. I'll make sure that I put these in the Google Drive as well. And in fact, let me go ahead and just move this one over. And this one I'll put in the full lesson for today. All right, so that's it. We'll wrap it up. We'll see you guys in the next lesson.